Hello, everyone. Today we will study the convolution integral of continuous time LTI systems. The second method in time domain analysis is the zero input response and the zero state response, which we will introduce in 3 parts. In the time domain analysis method, the system's initial state can also be regarded as a type of input excitation. According to the linearity property of the system, the system's response can be viewed as the superposition of the responses produced separately by the system's initial state and by the input signal. Among these, the output produced solely by the action of the initial state on the system is called the zero input response, denoted y sub x of t. The output produced solely by the action of the input excitation on the system is called the zero state response, denoted yf t. Therefore, the complete response of the system is y of t equals y sub x of t plus y sub f of t. The zero input response can be obtained by solving the homogeneous differential equation. The zero state response can be obtained using the convolution integral. Firstly, solving the zero input response. As the name implies, the zero input response refers to the output response when the input signal is zero, produced solely by the action of the system's initial state. The mathematical model of the system's zero input response is given by the following expression. It is evident that the zero input response has the same form as the homogeneous solution of the system's differential equation. The solution method is to determine the form of the zero input response from the characteristic roots of the differential equation, and then determine the undetermined coefficients from the initial state. Here, let us discuss the initial state and the initial conditions. Suppose the excitation is applied at t equals 0. The instant t equals 0 minus refers to the moment immediately before the excitation signal is applied to the system, while t equals 0 plus refers to the moment immediately after the excitation signal is applied to the system. The initial state of the system refers to the state of the system when there is no external excitation signal, reflecting the historical information of the system. The initial conditions in the classical method refer to the state of the system at t equals 0 after the excitation signal has been applied. In practice, the initial state of a system is often known first. For the zero input response, since there is no external excitation signal, the initial state and the initial conditions are equal due to the application of excitation. If the system exhibits a jump at the instant the excitation signal is applied, the initial state and the initial conditions are not equal. Next, let us solve the zero input response through an example. The problem gives the system's dynamic equation and the initial state, and asks for the system's zero input response. From the system's dynamic equation, write the characteristic equation. The characteristic roots are found to be S1 equals S2 equals minus 2, 2 equal real roots. The form of the zero input response is yx of t equals k1 times e to the power of negative 2t plus k 2 times t times e to the power of negative 2t. Substitute the initial state. Y of 0 minus equals yx of 0 minus equals k1 equals 2. Y prime of 0 minus equals yx prime of 0 minus equals negative 2 times k1 plus k2 equals negative 1. Solving for k1 and k2 and substituting back yields the system's zero input response. Since the observation time generally starts from t equals 0, append the condition t greater than or equal to 0 at the end of the expression. Next, solving the zero state response. As the name implies, the zero state response refers to the response produced by the system's external excitation when the system's initial state is 0. denoted y sub f of t. There are two main methods for solving the zero-state response of a system. 1. Directly solve the differential equation with zero initial state. That is, use the classical method introduced earlier. 2. Use the convolution method. We will focus on the convolution method. For linear time-invariant systems, the convolution method solves the problem by using signal decomposition and the properties of LTI systems. Idea of the convolution method for solving the zero-state response. Decompose any signal into a linear combination of unit impulse signals. Find the zero-state response of the system to a unit impulse signal. That is, the unit impulse response h of t. Using the properties of LTI systems, find the response to the linear combination of unit impulse signals. That is, the zero-state response y sub f of t of the system under any excitation f of t. We now give the definition of the unit impulse response of a continuous time LTI system. Under the condition that the system's initial state is zero, the output response produced when the system is excited by the impulse signal delta of t is called the impulse response of a system, denoted h of t. For an nth order continuous time LTI system, the impulse response h of t satisfies the following equation. Replace the input signal in the original system model's differential equation with delta of t, and the system's output is the impulse response h of t. Derivation of the convolution method for solving y sub f of t is as follows. The zero-state response of an LTI system to the unit impulse signal delta of t is the system's unit impulse response h of t. For an LTI system, by the time invariance property, when the excitation signal becomes delta of t minus tau, the response is h of t minus tau. By the homogeneity property, we obtain this expression. Note: here, the system is a function of time, and f of tau is treated as a constant. By the additivity, integration property, we obtain this expression. Therefore, the zero-state response of a continuous time LTI system equals the convolution integral of the input excitation and the system's unit impulse response. Y f of t equals f of t convolved with h of t. If the input signal is f of t, and the impulse response of a continuous time LTI system is h of t, then the system's zero-state response, y f of t, is given by the convolution of f of t and h of t, as shown in the formula. The zero-state response of a continuous time LTI system is the convolution integral of the input signal and the system's impulse response. This convolution integral is not merely a computational formula. It reveals the mechanism of interaction between the signal and the system in the time domain. That is, it describes the relationship among the input signal, the output signal, and the system's impulse response. Here we emphasize, although the system's impulse response is itself a signal, h of t can characterize the inherent properties of a system. Different systems have different impulse responses, and there is a one-to-one correspondence between a system and its impulse response. Next, let us solve the zero-state response through an example. Given the system's impulse response h of t and the input signal f of t, the zero-state response y f of t equals f of t convolved with h of t equals the integral from negative infinity to positive infinity of f of tau times h of t minus tau with respect to tau. Replace t and f of t with tau to obtain f of tau. Replace t and h of t with t minus tau to obtain h of t minus tau. Substitute to obtain the following expression. For u of tau, when tau is greater than 0, u of tau equals 1. For u of t minus tau, when t minus tau is greater than 0. That is, when t is greater than tau, u of t minus tau equals 1. Therefore, for the product of the two, t greater than 0 is required for it to be non-zero. When t less than 0, the entire expression is 0. The integration range for tau is from 0 to t. Solving the integral readily yields the expression for the system's zero-state response. For an LTI system, when the input signal is a unit step signal, the system's zero-state response is defined as the unit step response, denoted g of t. Substitute into the system's differential equation as shown in the figure. There are two methods for solving the step response. 1. Directly solve the differential equation, classical method. 2. Since the unit impulse signal and the unit step signal are related by differentiation and integration. For an LTI system, the unit impulse response and the unit step response are also related by differentiation and integration, as shown in the formula in the figure. Let's illustrate this with an example. Given the system's unit impulse function h of t, we can make use of the relationship between the unit impulse response and the unit step response to conveniently determine the system's unit step response. Let's have a summary about this lesson. In system analysis, we have studied the second analysis method, decomposing the complete response of the system into the sum of the zero input response, produced solely by the initial state, and the zero-state response, produced solely by the excitation. The zero input response is obtained by solving the homogeneous differential equation, that is, by the classical method. The zero-state response can be obtained using the convolution integral. Finally, please complete the following exercises to consolidate the content of this lesson.